So in 10.4, we want to find the areas of regions that are bounded by polar curves, and we want to find how long a polar curve is. Now we have one technique that will actually already work. We could just rewrite it as a parametric curve and then do what we learned in 10.1 and 10.2. So a polar curve can always be parameterized. So we have one technique for integrating. That is for finding the area under the curve. But there's a better way. I mean, the technique I'm talking about would be to write this as x equals r cosine of theta, and y is equal to r sine of theta, where r is now some function of theta. So you could write this as f of theta cosine of theta and f of theta sine of theta. Then you have x as some function of just theta, and y is a function of just theta. And then you could use this area formula we learned back in 10.2 of the y function, which is f of theta sine theta, times the x function, take the derivative of it, prime d theta. But that usually turns out to be a mess, and the formula I'm going to end up showing you is a whole lot simpler than that. Not that we're always afraid of mess, but that's too messy, because there's an easier way. There is a better way. And the better way is to deal with this the way that we would build integrals from when we first introduced integration. What I'm going to do, in fact, to kind of give you an idea of this, let's start down here in this space. So where it says consider a polar curve, so let's say we've got our horizontal axis right here. Let's say at some theta, maybe this direction, that's theta equals alpha. Actually, I'll just use A. Just A. And then maybe up here is another theta. This is theta equals B. Let's say we've got some curve right here. That's R is some function of theta. And what we want to know is we want to know what's that area inside here. Okay, so there's our origin. Straight line out this way is the first theta. Straight line out this way is the second theta. For every theta in between, our radius of our function is given by some formula, and we want to know what that area is inside there. I mean, it's almost the same idea as when we start with, you know, an area that goes from A to B, and we wanted to know the area underneath there. That was the rectangular way of doing things. Well, now we're dealing with polar curves, so we're sweeping out an area as theta moves instead of just moving along the x-axis. Now, what we did back in this day and age, whenever we were finding the areas, is we divided that up into pieces, right? And then we created a bunch of little rectangles. So now what we're going to do is we're going to divide this region up into little pieces, and instead of having rectangles, we're going to have something called sectors. So in order to do that, we need to remember what the area of a sector is. And what do I mean by sector? I mean take part of a circle. Okay, so in your mind, picture that I've got a circle. I'm right here. I'm looking at what is this area right there. Okay? If this is theta, and this length here is r, there's a formula for the area of a sector. Anybody happen to remember the area of a sector formula from geometry?
8 over 160 squared.
Theta over what?
Oh, 360. I guess I'm 160.
That's if it's in degrees. We only need it, it's just theta over 2 r squared. If you're in radians, you don't have to convert first to degrees, or vice versa. You don't have to convert from degrees to radians. If you use 1/2 theta r squared, that's the area of a sector. Very good remembering that in degrees. I don't even know that formula. What I have to do in my head is I have to remember that if theta was 2 pi, that is, if it was the whole circle, I know the area. It's pi r squared. Okay? But what is theta for a whole circle? What is, how much rotation do you have to go all the way around? 360 degrees, or in radians, 2 pi. Right? So I need that the thing out in front of r squared needs to be pi. So if you have 2 pi, to get to pi, I got to multiply by 1/2. So that's how I remember it's 1/2 theta r squared. So whatever theta is, if theta is in radians, then your area is 1/2 theta r squared. So here's what we're going to do. We're going to partition the range of theta. And this is where I wish I had drawn it for you, but you're going to have to do the best you can following the same picture that I've got. So let's draw my horizontal axis here. Let's draw theta equals A here. This is theta equals B up here. This is my curve. R equals F of theta. Now what I want to do is I want to divide this into equal regions. Like that. Okay? So that the change in theta here, that is maybe this right here, I'll draw a line there, that would be a delta theta. Okay, so I'd call this like theta sub 0, theta sub 1, theta sub 2, all the way around. Just labeling each one of those thetas. So kind of like we used to do up here with the rectangles, we divide them equally up. Now we're dividing this range into equal arcs of length or of rotation of angle delta theta. Okay? So for every one of these intervals, which I'm going to call theta I to theta I plus 1, I'm going to pick one theta inside that interval. I'm going to call that theta I star. So I get to do this in color. You're going to have to do this just with what you've got there. I'm going to pick one theta in here. I'm going to call that theta sub I star. Now the radius, that is this distance in red, would be r is equal to f of theta sub I star. Because that's how far out you go to get to that curve. Since r is f of theta, if I plug in theta I star, that's going to give me that distance that I just drew right there. So now what I'm going to do is I'm going to create a sector of a circle of that radius. Again, I'm sorry that's probably hard to draw on your own. It's hard enough for me to draw with this tablet. But notice now how this region is now going to be made up of a whole bunch of these little sectors. Just like it used to be made up of a whole bunch of rectangles, now it's a whole bunch of sectors. Now, what I'm going to do is I'm going to add them all up. Now, what's the area of that one red piece that I've drawn right there? By this formula up here, it'll be 1/2 times whatever the theta is, that is this distance or this measure of an angle here, which is delta theta, times the radius squared. So A sub I is going to be 1/2 delta theta times f of theta I star squared, because that's my radius. I'm not even going to write that in there, right? This piece right here, from right here, is my radius. That's r squared. And then my angle, delta theta, is what I'm putting right there. Or, to write it out just a little bit simpler, 1/2 f of theta I star squared times delta theta. And you start to see this is going to turn into a Riemann sum, which we can then take the limit of and end up with actually a very simple integral. So the total area, which I'm going to label as A, would be the sum of all n of these sectors, all of this size. For I goes from starting at theta 1, theta 2, theta 3, all the way around. So it's going to be 1/2 of this, f theta sub I star squared delta theta. Then we do the calculus, which is essentially this. Take it to the limit one more time. So the total area, say A sub r for that region R, will be the limit as n goes to infinity, the sum from I equals 1 to n of 1/2 f of theta I star squared delta theta. But yay, that is a, I can't spell his name right, sorry. Riemann sum. So the area is the integral from A to B of 1/2 f of theta squared d theta. When you take the limit of this, you just replace the theta I star with your variable, replace your delta theta with d theta, and then the range of your theta. Or you can write it sometimes written as 1/2 r squared d theta, where r, you now remember, is the function f of theta. Which is nice because, I mean, there's some symmetry here. This looks almost exactly like the sector formula. It's 1/2 r squared theta. In our case, now we're going to integrate over theta, so 1/2 r squared d theta as theta goes from A to B. So instead of having to go back through and parameterize it and then take the derivative and plug it into, you know, this guy that I had up here, all you have to remember is to take an area of a polar region, integral from A to B, 1/2 r squared d theta. I'm going to come back to this in just a second, but let me just kind of look ahead. In this case right here, I'm asking you to find the area inside the polar curve r equals theta from 0 to 2 pi. All I've got to do is use this right here as my f of theta, or as my r over here, and it's a real easy integral problem. Now, the one other thing that I could do to make this a little bit more interesting is to consider the region between maybe two polar curves. Let's say we've got a region swept out from theta equals A to B. Let's say this out here is r equals some function f1 of theta. Let's say we've got another curve, which I'm going to call r equals f2 of theta. And instead of wanting to find this whole region inside here, I want to find the region between the two curves. And the area is just the difference between the two regions, right? It's like this minus this. Actually, I drew that the other way. That's sloppy. right? This is the integral of 1/2 f1 of theta squared, and this region inside here would be the integral of 1/2 f2 of theta squared d theta. See what I mean? You just take the big region minus the little region to get the region in between. So if you're asked to find the area of a region between two polar curves, then all you have to do is basically this. You're going to take the integral from A to B of 1/2 f1 of theta squared minus 1/2 f2 of theta squared d theta. Actually, I think the book actually writes this as A to B and then 1/2 and then factors this out. So you got f1 theta squared minus f2 theta squared d theta. Either way, just factoring out the 1/2 is the only difference between those two. Okay? So for areas of polar curves, you got to remember this formula, and if it's between two curves, you got to remember this formula, and that's it. It's always helpful on any problem to graph it first, just so you know what you're looking at. So if I wanted to actually know what this polar curve looked like, I would go into Maple or Wolfram Alpha and graph it. So if I went to Maple to graph the one that you have there, plot t, or theta, for t goes from 0 to 2 times pi, chords equal polar. So looking at the next example, I want to find the area inside this spiral. So do you know what I mean when I say inside of it? It means between any point and the origin. If I were to graph this, maybe color this in with my finger a little bit here. I'm looking at this region inside here. Right? I want to know what's the area there. So if you're given a polar curve and you want to find the area, it's integral from A to B, 1/2 r squared. So let's do that. Let's go back over here. It's always helpful to graph first. I'm just going to draw a rough sketch of it. It looks something like this. They gave us the limits. So the area is the integral, 0 to pi, 1/2 times r squared. R in this case is just theta. So theta squared d theta. And then there's nothing special from that point forward. It's just a basic integral. In this case, a very basic integral. You can just leave the 1/2 there. What's the integral of theta squared? With respect to theta. Like that? Does that look good to everybody? From and then we just plug those in and subtract. So you get 2 pi cubed over 6 minus 0 cubed over 6. Right, you see that that's just theta cubed over 6. That's where I get that. that's 0. This gives me 8 pi cubed over 6, or cancel a 2 out of top and bottom, 4 pi cubed over 3. There's your area. You can check, I mean, you can go straight from here to here with, say, Wolfram alpha. I'll give you any range of problems. Some as easy as this one, some may be a little bit more difficult. This next one, it's actually not that bad to integrate. In fact, I think this one turns out to be real easy to integrate too by hand. But like I said before, what I care most about seeing you do is set up the integrals to get the area. Are we okay with that example? I mean, it's real easy, right? You just plug it in. Once you know you're finding the area of a polar region, it's 1/2 r squared d theta. So what would be the integral on this one? Even if I didn't graph it first, what's the integral look like? Zero to pi over 4, 1/2. It's this squared, right? Which is just okay. Again, use integral 1/2 r squared d theta. So I just squared this to get that. Anybody see why that one's real easy to integrate? Hint, use a substitution.
U is sine, du is cosine.
So here's u, and here's du. So you have integral of 1/2 u du. And you always change 3 things, right? Change your limits. What's sine of 0? And what's sine of pi over 4? Root 2 over 2. Okay, so this becomes 1/2 integral of u is over 2 from 0 to square root of 2 over 2. So that's square root of 2 over 2 squared all over 4 minus 0 squared over 4, right? So that's 0. What's root 2 over 2 squared? 1/2 divided by 4.
Yeah, 1/8.
Right, invert and multiply.
Okay, I flipped the wrong.
Okay. So it's 1/8. That's the region. Now, if I went back and graphed it, so I went back over, say, to Maple, and I did, just to see what the curve would look like, plot square root of sine of t times cosine of t. T goes from 0 to 4. Towards equal polar. So we're looking at, I'm just going to draw on this real quick. If I drew a line right there, right, everything inside here is that area right there is 1/8. Okay? Excellent. All right, let's do one more area because I want to do at least one that has two curves in it. So I want to find the area inside r equals 2 cosine of t, and I should have said here, outside r equals 1. Now, I don't know if it's in this textbook. I remember whenever I taught trig and we covered polar equations, there was like a table that listed some common polar functions, things like circles, ellipses, roses, lemniscates, and cardioids, and different things like that. I remember that there was this r equals a cosine of theta, which always looked like it's a circle here where the radius is actually, that's a over 2 right there. Now I could go plot this on Maple. Turns out that goes from theta, goes from 0 to pi. Can you tell me what r equals 1 looks like if you graph it as a polar equation? Circle, radius of 1, centered at the origin, right? Because it's always, no matter where you are, a distance 1 away. So let's graph both of these on the same graph by this rule over here. So first of all, you've got, if I go over 1, and up 1, down 1, I've got r equals 1.
It's terrible.
Now the other one, 2 cosine t, starts at 1, 0, and it's still a circle of radius 1. Like that. In fact, I'm going to go graph it in Maple. I can do two curves at once by putting them inside brackets. Plot bracket 1 and was it 2 times cosine t? T goes from 0 to, we'll do 2 pi. I got to get 2 pi in to get the 1 all the way around. If I change that to 1 to 1. All right, there's the shape that I just drew. Okay, I could plot them each separately, or I could plot them both at the same time. Now, what region is inside of 2 cosine t and outside of 1? It's this inside here, right? I want to know what the area of that region is. Okay? Well, notice then, if I can find out what this and this theta is, then what I'm doing is I'm measuring from the outside curve to the inside curve. This is like my F1. This in here is like my F2. Right? I'm taking the outer region minus the inner region. But I got to figure out my intersection point in order to do that. Okay. I'm going to have to exit out of that picture, and I'll come back over into OneNote and I'll draw it there. Right? It's this region in here. But first I've got to find the intersection. Because I've got to know what's this theta And what's this theta up here? Then I can just integrate from this one up to this one. So how do you find the intersection points of two curves? Set them equal to each other. Set this equal to this. 2 cosine of t equals 1. So cosine of t, or theta, is 1/2. I think I meant to put theta in here, but I'm going to leave it as t since that's what you have in the problem. But it's the same idea. So I'm looking at, I want the adjacent over the hypotenuse to be 1/2. So I'm going to use a 2, 1, square root of 3 triangle down here and one up here, right? Which makes that 60 degrees or pi over 3. This one down here, now since I want to go from the bottom angle to the top angle, I'm going to use negative pi over 3 for this one up to positive pi over 3. Instead of using 5 pi over 3, if I went from 5 pi over 3 to pi over 3, that's actually going backwards from here around here. But what I really want to do is go from the bottom one up to the top. So that's why I'm going to use negative pi over 3 to positive pi over 3. Again, I'm solving that by using my trig, using my 30, 60, 90 triangles when I know the cosine is 1/2. That's that short side over hypotenuse, which makes this angle in here the 60 instead of the 30. Because cosine's adjacent. Okay, now that means I'm going to go from the integral from negative pi over 3 to positive pi over 3 of 1/2, and remember now outside function squared minus inside function squared. Okay, so this curve out here was 2 cosine t.